Let's continue with the next property, which is third one. Let us take that to be frequency shifting. Okay, so frequency shift, or we say shifting in frequency domain. Okay, so shifting in frequency domain. So what does it say? Let x of t has x of j omega as the Fourier transform, then e power j omega naught t x of t. So let us call this signal to be x1 of t. Okay, so what is that we have done here? We have multiplied our signal x of t with whom? E power j omega naught t, and we called that signal to be x1 of t. So this fellow will have x1 of j omega as the Fourier transform, which is given by x of j omega minus omega naught. Means what? You have to shift the frequency, or you should shift the Fourier transform by omega naught units. Okay, so when is that possible? If you multiply the time domain signal with whom? E power j omega naught t. So we will take the proof of this. Okay, so what do we want? We want the Fourier transform of x1 of t, which we call it as x1 of j omega. So what will be our x1 of j omega? That is nothing but integral minus infinity to infinity x1 of t e power minus j omega t dt. Okay, so let us substitute our x1 of t, which would be equal to integral minus infinity to infinity x1 of t is what? It is e power j omega naught t x of t multiplied with e power minus j omega t dt. Okay, so this you can easily see that this is equal to how much? So we can write it as integral minus infinity to infinity x of t multiplied with e power minus j omega minus omega naught into t dt. Correct? Why I took e minus j out? If you take minus j out and t this side, so you'll get omega minus omega naught as the common term. So you can easily see that these two are equal. But if you look at this equation little bit carefully, what is it you see? This is looking like again analysis equation, except that omega is replaced with omega minus omega naught, and hence this should be equal to how much? This is our x of j omega minus omega naught. Okay, so what did we prove? We have proved that if you multiply your signal x of t with e power j omega naught t, what will happen? In frequency domain you have to shift the Fourier transform by omega naught units. Okay, so just to put this in block diagram notation. Okay, so what is that we have done? We had a signal x of t, and this fellow is multiplied with e power j omega naught t, and this fellow will give you x1 of t as the output. Okay, and what happens to the Fourier transform? I am writing below. So this fellow will have x of j omega. So this fellow will have x1 of t is what? x1 of t is nothing but x of t multiplied with e power j omega naught t, and this fellow will have x1 of j omega as the Fourier transform, which is nothing but x of j omega minus omega naught. Okay, right, so in a similar fashion you can prove that e power similarly e power minus j omega naught t x of t will have x of j omega plus omega naught as the Fourier transform. This is easy to prove, so I'll leave it as homework. So okay, because as I put a question mark, you prove this as homework, just like we have done above. Okay, so Now let us add these two fellows. So what do I mean by that? So e power plus j omega naught t x of t plus e power minus j omega naught t x of t. So what will happen? The corresponding Fourier transform would be, first fellow will have x of j omega minus omega naught plus second fellow will have x of j omega plus omega naught as the Fourier transform. But if you look at the left hand side, x of t is common, and if you take x of t common, you will get e power j omega naught t plus e power minus j omega naught t, which is nothing but 2 cos omega naught t. So this implies 2x of t cos omega naught t, correct? So 2x of t cos omega naught t will have x of j omega plus omega naught plus x of j omega minus omega naught as the Fourier transform. So similarly, what will happen if we subtract? Okay, so I'll write down that also. So what do? I will take e power j omega naught t x of t. Now I subtract, okay, minus e power minus j omega naught t x of t. So this fellow will have, because we are taking subtraction here also, on the right hand side also we have to subtract. Why? Because of linearity property. So e power j omega naught t x of t will have x of j omega minus omega naught minus this fellow will have x of j omega plus omega naught as the Fourier transform. But if you look at the left hand side, what is this equal to? This is equal to 2j x of t multiplied with sine omega naught t. So this fellow will have this as the Fourier transform. So if you want to do some algebra, you can send j this side, so that will, or you multiply throughout with minus j, correct? So if you multiply left hand side and right hand side with minus j, what will happen here? So j will come out, so I'll write down that. So see, this implies 2x of t sine omega naught t, correct? So this fellow will have what as Fourier transform. How do you get this? You multiply with minus j. In time domain, if you multiply with minus j, in frequency domain also you should multiply with minus j. Why? Because Fourier transform satisfies linearity properties. If you multiply with minus j, I'll put j out. So if you multiply with minus 1, what will happen? This fellow will become plus and this fellow will become minus, and hence you will get x of j omega plus omega naught minus x of j omega minus omega naught as the Fourier transform. Okay, right. So you can send 2 again this side. Even for this also you can send 2 that side, let it be there. Okay, but these two combinedly, okay, 2x of t cos omega naught t and 2x of t sin omega naught t, so both are called what? Modulation property. Your wish, you multiply with cosine term or sine term, but we call both of them to be what? Modulation property. Okay, so especially this one, which one? 2x of t cos omega naught t will have this as the Fourier transform, and 2x of t sin omega naught t will have this as the Fourier transform. These are called what? Modulation property. Okay, and this is also modulation property. We call it as modulation property. But how did we derive this modulation property? We derived this from frequency shifting property. Okay.